Okay, we are going to start off with the definition of the fundamental counting principle. Because I'm sure that they will ask you vocabulary questions over that on your homework, which means those will be on the review, which means those will be on the test, guys. In a sequence of n procedures, if the first can occur in case of one ways, the second in case of two ways, the third in case of three ways, and so on. The total number of ways the sequence of procedures can occur is case of 1 times case of 2 times case of 3 all the way to case of n. Okay? Now, I'm going to give you kind of an example of what it's talking about. Okay? Let's say that we go to a lot to buy a new car. Okay? And here are the choices. A small lot, this is all we can do here. It's all they can do. It's all we can afford. Okay, so we're not changing the scenario here. So if we go to buy a new car at this car lot, we can either buy a 2-door car or a 4-door car. Okay? Now, of those 2-door cars and those 4-door cars, I can get a 2-door car or a 4-door car in the color of black, white, or red. Okay? Then I have these 2-door cars, these 4-door cars in black, white, and red. And then I have the option of getting them in leather, the interior in leather, or fabric. Okay, so my question for you is how many different options of cars are there? Do I have to choose from on that lot? So I can do a 2-door or a 4-door, black, white, red of either one, and then leather or fabric in either one of those colors. So here's what I have to choose from. Here's how I determine how many cars there are for me, how many possibilities there are, okay? So I know it's either a 2-door car or a 4-door car, right? And from the 2-door cars, I have the option of black, white, or red, okay? And then each one of those black 2-door cars, there's one that has leather, and there's one that has fabric. Okay? Same for the white. There's one with leather, there's one with fabric. Same for the red. There's one with leather, there's one with fabric. Okay? Now over here, the 4-door car, we have the same option. We have black, we have white, we have red. I can get that 4-door car in black, white, or red. And then I can get that four-door black car in leather or fabric. I can get that four-door car, white car, in leather or fabric interior. And then I can get that four-door red car with either leather or fabric interior. Okay, how many different ways pretty much can I order my car there? How many different possibilities are there? 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I can have leather black two-door, fabric black two-door, leather white two-door, fabric white two-door, leather red two-door, fabric red two-door, right? Or I can have leather black four-door, fabric black four-door, leather white four-door, fabric white four-door, or leather red four-door, or fabric red four-door. Okay? So there are 12. How many possibilities? Okay, there are 12. Now, for every scenario, you don't want to have to do that. Okay? You don't have to write all that out. Write all the different options out. So what the fundamental counting principle is, what it says is, okay, first slot, how many doors are there? Different car doors. Pretty much. There's a two-door and there's a four-door, right? Two-door, four-door. So there's two different options, right? Okay? And it says, all right, on the color, how many colors are there to choose from? 3. And then it says, okay, on the interior, how many different choices are there? 2. And you just multiply all those together, and what do you get? 12. The answer you got, and you didn't have to write all of that stuff down. You didn't have to make the tree diagram, okay? That's what we're saying. That's what the fundamental counting principle says. So let's look at example 1. A discount paint manufacturer plans to make several different paints. The categories include color, red, blue, white, black, green, brown, yellow, type, latex or oil, texture, flat, semi-gloss, high gloss, and use indoor, outdoor. Okay? Question is, how many different kinds of paint can be made? Okay? All right, so first thing we need to do is we need to make a slot for each of our categories, okay? So I know I've got a color slot, then I've got a type, then I have a texture, and then I have a use, okay? So you've got a category slot for each one, okay? Now, you ask yourself, okay, well, how many different color possibilities are there? How many we got there?
7.
Good. How many different types can I have? 2. Good. How about texture?
3.
Good. And how about use?
2.
Very good. Now, we're going to multiply all those together. And you can take your calculator and you can say 7 times 2 times 3 times 2. When we multiply all those together, that should give me 84. So we have 84 different kinds of paint that can be made. You don't have to write that little part there if you don't want to. All I really need is the 84. I write it so you know what we're talking about. Okay? All right, let's try another one. Let's look at example 2. Example 2 says the lock on a storage facility is controlled by a keypad containing digits 1 through 5. Okay? A says how many 3-digit codes are possible if digits can be repeated. Okay, that right there, the can be repeated is important. Okay, so we want a 3-digit code and we want to use the digits 1 through 5 for that 3-digit code. They're asking me how many different 3-digit codes are possible using those 5 digits. And the digits can be repeated. So guys, what that means is we could have 333, 222, 111, 555. Okay, of course you also have 543, 512. Now, do we want to list all those out? No, we don't. So here's what we do. We've got this storage lock, and I know I've got to put a number in the first slot, I've got to put a number in the second slot, and I got to put a number in the third slot. How many different possibilities do I have in that first slot? 5, because I can use a 1, a 2, a 3, a 4, or a 5, right? Got 5, okay? Now it says I can repeat. So it doesn't matter what I pick for the first one, how many do I have available for that second slot? Still got the same 5, right? I still can put in a 1, 2, 3, 4, or 5. How about in that third slot? 5, right? So 5 times 5 times 5 gives me 125. Okay, so there are a possibility of 125 different 3-digit codes that could go into that keypad using the digits 1 to 5. Okay. says how many different, let me fix that B. How many different codes are possible if digits cannot be repeated? Okay, so this time we cannot repeat the digits. So we got our slots again. So in that first slot, what are my possibilities of going in there? I have how many? 5 again, right? I can pick 1, 2, 3, 4, 5. Okay? Now, I can't repeat. So whatever I picked the first time, I can't use it again. So how many do I have this time? 4. I got 4 numbers left. And now in that third slot, I have 3. So I have a total, when I multiply that all together, of 60 different possibilities. So if we can't repeat a digit, the possible codes goes down, right? Okay. You guys haven't talked about it because, okay, so that's going to be fresh for y'all, the next part. The next thing that we're going to talk about is what we call factorial notation. Okay. It is denoted with an exclamation at the end of it. Now, this shows in factorial. I'm showing you the definition here. Usually there's a number there, such as 2 factorial or 10 factorial or 5 factorial. It stands for n times n minus 1 times n minus 2 times ... all the way to 3 times 2 times 1. Okay, one important thing that you do need to know and you need to remember is that 0 factorial actually equals 1. Okay, that is important. 0 factorial equals 1. Now, let me show you how we do these factorial problems. So in example 3, we have evaluate each expression. Okay, A is 6 factorial. Guys, all that means is I'm going to say 6 times 5 times 4 times 3 times 2 times 1. Okay? Well, it's easier for me just to multiply those together than to put them in the calculator. That's going to be a 30 times a 12 times a 2. And that's what, 360 times 2, which is 720. Okay. So 6 factorial is 720. B, I have 12 factorial over 8 factorial. Now, I'm going to write out, and I want you to watch what happens here. I've got 12 times 11 times 10 times 9 times 8, 7, 6, 5, 4, 3, 2, 1. And that's all over 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now, why do you think I scooted over and wrote them underneath themselves? Because they cancel out. They simplify down to 1. That is correct. 8 over 8, they cancel out. They make 1. 7 over 7 is 1. 6 over 6. 5, 5, 4, 4, 3, 3, 2, 2, 1, 1. So this is just really 12 times 11 times 10 times 9, which does give me, in the end, 11,880. Okay, we're going to do one more like that, and then I'm going to show you something. And you're going to go, why did you make us write all that out? I've got 6 factorial over 4 factorial. Okay. Some of you can see it in your head without having to write it all down. Who goes away? 4, 3, 2, 1, right? The only thing that's left is really 6 times 5, which is going to give me 30, right? Because this is so 4 and down cancel out because they're going to be there, both be there. We could have just said, well, that's 6 times 5, which does give me 30. Okay, let's take out our handy dandy multi-view, and I will split the screen so we can see both here. Okay. All right, so that first one says 6 factorial. Guys, you don't even have to really even know what it means. I shouldn't tell you that, but if I type in 6 and then I push the PRB button, not PBR for professional bull riding, PRB, okay? And then I push the PRB. It's in the second row, second column. It highlights up red for you. And then 3 is my factorial, okay? So I go down, I hit 3. I have 6 factorial, I hit enter. I see I get 720, which is what I got. And I don't even have to type in all the different numbers, okay? My next one, you guys know how to use a stack fraction by now because we've done the finance unit. So I stack my fraction, I put in 12. I go to PRB, I pick 3. I go down, I say 8, PRB 3. 12 factorial over 8 factorial does give me 11,880. I don't have to type anything else in. I just literally type in the problem, okay? Now, you will, on your homework, run into a problem of your calculator will tell you that you have an overflow error. So you have to do a little thinking. I'm going to do 6 factorial over 4 factorial, and then I'll show you. 6 PRB 3 over 4 PRB 3. And that does give me 30, so we're good to go. If I had something like 160 factorial over 155 factorial. Okay, so you're perusing along here, and I go 160 PRB 3 over 155 PRB 3, and I get an overflow error. Okay, what that means is the calculation's too high for the calculator to handle it. Is what's happening. And the part that's too high for it is the 160 factorial. It is literally trying to multiply 160 times 159 times 158 all the way down to 1 and do the same thing on 155. Guys, you can still get your calculator to do it. Think about it. If I have 160 factorial over 155 factorial, who all cancels out? 155 down. So this is really 160 times 159 times 158 times 157 times 156. Now, I think your calculator can handle that one. Okay, so if I clear it and I go, all right, say 160 times 159, 158, 157, 156, 6. Okay, now, it doesn't throw you an overflow error, but it does show you something. What's that in? What's that called? Scientific notation. Very good. We get, when we multiply this out, we're getting 9, and I'm going to write it all out because we do need to address this because some of you don't remember, and the textbook assumes that you do. times 10 to the 10th, okay? All right, that little 10, let me write it better. The exponent 10 tells you how many places to move that decimal and what direction. If the exponent is positive, I move to the right, okay? So we're going to say positive exponent, move right. And you move the decimal, whatever the number on the exponent is, okay? Move 10.
There's only 9 numbers, so
Okay.
just assume the last is a 0.
That's what, yes, because the calculator can only display that many digits. So when we go to move this, and I'm going to rewrite it so you can see what happens. 384, did I get them all? 844, 608, 384. And we're supposed to move 10, so I go 1, 2, 3, 4, 5, 6, 7, 8, 9, and I got to move one more, 10. So I've got an empty spot there, and in that empty spot, I have to put a 0. Okay, so this number is actually 984 446 083 840. So we get 984,446,083,840 possibilities on whatever this was, this factorial. Okay, that's what that number really is. But when you get that overflow, because you'll get an overflow with a 160 factorial over 155 factorial, put it into what that's left being multiplied together, it will give you an answer. It's probably going to be in scientific notation. You can convert that to the appropriate answer. I'll make it bigger. Parker, hold on. There you go. Okay. All right. An arrangement of n distinct objects in a specific order is called a permutation of the objects. Okay? Here's the important part of this. Order matters. Because in 10.3, we're going to talk about a combination, and in combinations, order doesn't matter. If any of you have sat in any kind of statistics class, AP stats class, I'm sure you talked about permutations and combinations in AP stats. Typically you do. Yeah, there's always a tiny probability section. And you have to be able to read the problem and know whether to pick NPR or NCR, whether it's a permutation or a combination. But we get to that on Tuesday, the other. Okay, so let's look at example 4. Example 4 says A. Yes. Yep, I can go up a little bit. List all the orders in which you could line up 4 photos in a frame. Okay? What this is I'm sure some of your mothers have it in their houses. You may even have one like it. It's a big photo frame, and it's going to allow you to put 4 different pictures in there. Sometimes you can put more than 4. It's various amounts. It has some kind of decoration on it. Okay? So you've got 4 pictures, and you want to know how many different ways you can arrange those pictures in that picture frame, in the slots that we put them in. Okay, I'm going to let A be photo 1. B, of course, is photo 2. C is going to be photo 3. And D is going to be photo 4. Now, the main reason we go through this is in case they make you list something like this, and it's also to show you don't want to have to go to the effort to list all those every time that you're trying to count up how many different ways you can do something. Okay, it's a lead into permutations. So, I start off with, and here's how I do this, process it in my head. I start off with how many different possibilities can photo A be first? Okay, photo A is going to be first. So I, of course, could have A, B, C, D, right? Then I take D in my head and I move him to the other positions. I leave everybody else the same. So A, B, D, C, of course C has to move. And then I have A, D, B, C. Okay? Then, look guys, I have an AB combo. Now I have an AD combo. Well, list the other AD combo. That'd be CB, right? So I got an ABCD, an ABDC, an ADBC, and an ADCB.
ACDC.
Yes, now we have to do an AC. You can't do DC because you can't use the same picture over there, okay? So I got to have an ACBD and then an ACDB. Okay, that's all the ways we can arrange those 4 photos with A getting to be first. Okay, let's do B. Guys, if I have 6 with A first, that means I'm going to have 6 with B first, I'm going to have 6 with C first, and I'm going to have 6 with D first. Okay? Order matters here. Order matters because if you are a sibling, if you're one of many, and by many I mean 3 plus, not 2. If it's just you and one other person, that don't count as many. I got 4 kids. Okay? And I'm going to tell you right now, out of those 4, there's at least 2 that are going to look at that and go, why did mama put her first? Usually it's the 2 other sisters that look and go, why did mama put her first?
She's a favorite.
I feel that I have
Yes,
4 other siblings.
because you have and you have a twin. It's my twins. One of my twin girls will look and go, how come mama has more pictures of the oldest sister on the refrigerator than us? And she'll include her own twin in there, and she'll go, than us. And, of course, they currently expect me to have more pictures of the baby on there because even though the baby's like nearly 20, he is the only boy. So, and he's the last one. So they know Cody's going to have more pictures, but they don't want to see that older sister with more pictures than them. And they don't want her first either. And I will cut that out of the video. But in case they ever hear it. Okay, so that's with the first one there. All right, so we're going to have 6 with B. I'm just going to go ahead and write that down. All right, so I could have BACD. I could have BADC. Well, I could have BCAD. I could have BCDA. I could have BDAC. I could have BDCA. I kind of did it a little different this time. I did all my B's, then the 2 A's, 2 C's, 2 D's. And I then switch the other, okay? Let's do C. C, 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 C. We know we need an AA, a BB, a DD. It's probably easier if we just do it like that. Then that'll be a BD and a DB. Okay. There's an AD and a DA. Okay, now I'm on D. Who do I need? AB and BA. Don't nobody want to be writing all that out. You don't want to write it out right now, and I'm just telling you what to write out. You sure don't want to have to think about it. Okay, and let's do our last one because it did ask us to list them all. I'm going to do an AA, BB, CC, BC, CB, AD, oh not AD, AC, CA. Okay, let's see, I'm on C, so that means I have AB and BA. That's all of them, guys. How many are there?
A lot.
A lot. There's just 24, okay? So there's 24 different ways I could arrange those 4 photos in that frame, okay? Let's look at B. B still has to do with this photo frame, okay? And I will, if you're not done writing all the choices out, write down 24 and then I'll go back at the end of the lesson and put it up there if you need it. B says use the fundamental counting principle to find the number of possible orders and make sure it matches the answer to part A. Okay? Okay, so this is back here. Here's photo 1, photo slot 2, photo slot 3, photo slot 4. Okay? We can't repeat, guys. We only have 4 physical pictures. How many different pictures do I have to put in slot 1? 4, right? Okay, anchor that one down. How many do I have now for slot 2? 3 to choose from. How many to choose from for slot 3? 2, and then the last one, okay? And if I multiply all that together, 4 times 3 times 2 times 1 is 24. And sure enough, 24 is how many different ways we got in part A. Okay? Now, you will notice 4 times 3 times 2 times 1 is really, I know it's 24, but how could I have written that?
For, what you call it?
Exclamation point, yes. 4 factorial, good. This is really 4 factorial. Now, here's what this says. Here's why we show that. The number of permutations of n objects using all the objects is n factorial. That's going to become kind of important because we're going to, in a little bit, we're going to say we've got 10 objects, but we're only choosing 2. How many different ways can 2 people be chosen from 10? Okay? Where order matters. Okay, example 5. In how many different orders can the 14 basketball teams in the Big Ten conference finish? And the book went on to talk about, it's called the Big Ten, but there's actually 14 teams. Yeah, whatever. I wasn't really worried about that. What they want to know is in how many different orders can the 14 basketball teams come out? So how many different possibilities are of ranking those 14 teams is what they're saying, okay? So we are taking 14 objects, and how many objects are we choosing? It's called the Big Ten Conference, but we're not choosing 10. We're ranking all 14. So we take 14 teams, we're ranking 14 teams, is what it's saying. How many different possibilities do we have of team rankings, is what it's asking. Well, no, it's 14, choose 14. So let's think about it.
Times 14.
It's actually 14 factorial, and here's why. We got 14 teams, right? 1, 2, 3, 4, 5, 6.
Already putting one in first place, it can't be in 14th place.
That's right. So I have 14 choices in that first place slot, right? Second place, I'm down to 13 possibilities. Third place, 12. Fourth place, 11. Fifth place, 10. Sixth place, 9. 8. 7. 6, 5, 4, 3, 2, 1. Okay? There's only going to be one person left for last place, right? Okay? What we wanted you to see here is that we have 14 objects. We're choosing all 14. So you're going to use 14 factorial. If I go over here to my calculator and I type in 14, use the PRB button, 3, factorial, you find, here's another, it's showing you in scientific notation. So somebody gonna have to split view. Actually, I can see it. Okay, so I wind up getting 8.71782,912 times 10. I'm leaving a little space there in case I need to add some zeros, times 10 to the 10th. Okay, so from what we did earlier, I'm going to take that decimal and I'm going to move him which direction and how many?
All right.
How many? 10. To the, to the right, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This time, how many zeros I got to put in there? 2. Okay? So this winds up being 8, 7, 1, 7, 8, 2, 9, 1, 2, 0, 0. 1, 2, 3, 1, 2, 3. So there are 87,178,291,200 different ways we could order those 14 teams. Okay? 87,178,291,200 different ways we could order those 14 teams. Now, generally, when y'all, I'm assuming this probably goes into like March Madness stuff. Like, is that what this kind of gets talked about? I don't know. But generally, you know where people that actually wager money on those, they know who's going to come out last. It's pretty much a question of who's in that top chunk. You know, who's number 1, 2, 3, 4 kind of thing. Okay? All right, that is example 5. Yes, it was. Example 6. How many different ways can a manager and assistant manager be selected from a department consisting of 10 people? Okay? Now, how many different ways can a manager and assistant manager be selected from a department consisting of 10 people? Here's the thing. Order matters here, right? Okay? Order matters. And can anyone repeat? No, because if I'm chosen as manager, then I can't be chosen as assistant manager, even though probably some of the places you work, whoever the boss is tries to be the bossiest boss. Anyway, but we won't go into that. Technically, they have 2 different jobs. 2 different people should fulfill those jobs. Okay? No repeats. All right, so how many slots do we have? 2. We have the manager and we have the assistant manager. Okay? How many people do we have to choose from for the manager spot? 10. So then that leaves how many for the assistant manager? 9. So there's 90 different ways the manager and assistant manager can be chosen out of 10 people. 10, choose 2. Pay attention to that little phrase. 10 objects, you choose 2. Okay? How many ways? So, let's write a definition and we get a new formula. The order of selection is important. And no repetition. I think I misspelled that yesterday too. Is allowed. Okay, those 2 things are very important right there. We call such an arrangement of objects a permutation of n objects taken R at a time. And it's written like this. There's this little n, there's a P, and there's a R. Okay? So n equals the number of objects. R is how many we are taking. Okay? Now, we can express this and we can find the answer like we had 10 people we were choosing to be the manager and assistant manager. And we have a formula for that. That's going to be n factorial over n minus r factorial. Okay? Now, let's think about up here. We didn't have to make too many slots. We didn't have to do a whole lot of multiplying. We could have, on example 6, gone, okay, we have 10. We're taking 2. This is really 10 factorial over 10 minus 2 factorial. Okay? That would have given me, well, that's 10 factorial over 8 factorial. Who's going to cancel out? 8 and down, right? So that would have left me with just the 10 times the 9 right there, which equaled 90. Okay? Right? And you're going, well, that took longer than saying 10 times 9. Yes, it did. But sometimes it won't. Such as in example 7.
Can I get that top one?
Yeah, give me just a second. That one right there, okay. Example 7 says how many 6-letter passwords are there that use only lowercase I know, I haven't added it there. It's a kid from a different class down in a different college. Are there that use only lowercase letters with no letter repeated? Okay? How many 6-letter passwords are there that use only lowercase letters with no letter repeated? Okay, so the first thing we need to do is we need to make sure this is a permutation. Okay? Nobody's repeating, and order does matter because it's a password, right? So the order of the letters does matter. A, B, C, D is not the same thing as B, A, C, D, right? Okay, so order matters and we're not repeating, so we can use our formula up here, our NPR, but we got to know a couple of things. What's N? 26, good. Whoever said that, thank you. N is 26 because there are 26 letters in the alphabet. We're only using lowercase. If we were using upper and lower, then it would be 52. Right? Okay? Now, R is the number that we're choosing. What's R? 6. Good. So I have 26 P6. The P stands for permutation. This is a permutation. I have 26 letters. I am choosing 6 of them. I want to know how many different passwords there are. Okay? So I've got 26 factorial over 26 minus 6 factorial, which equals 26 factorial over 20 factorial. You can put that in your calculator. And if we go over here and we put that in our calculator, and I'm betting it won't pop for you. Nope, it didn't. There we go. Okay, so I've got 26 PRB3. Whoops, I forgot to do my stack first. 26 PRB3 over 20 PRB3. I get 165,765,600 different possible passwords, 6-letter passwords, okay? 165,765,600. Okay? Now, some of you may have noticed that when you push the PRB button, what do you see there?
That there.
Number 1, okay? And that number 1 is nice. Because here's what we can do. I'm going to show you how to use it. You don't even have to know this formula or be able to use the formula, guys. Because we let you use a calculator. So you can literally go, what do you put in first? What's the first number that's there? N, right? So your calculator, he's not as smart as like an 84, so you have to help him out a little bit. You got to go, well, 26, you got to start off with what that first number would be, 26, that's my number of objects. Then we go to PRB 3, okay, not 3. PRB number 1, because that's got my NPR. All right, so that says permutation, the P's for permutation. And then how many am I choosing? 6. And you get the same answer, guys. Okay, so truth. What you have to be able to do is understand that they're talking about a permutation versus what we call a combination, which we'll talk about combinations on Tuesday. Okay, so you got to understand it's a permutation so that you're using, what was that, number 1? And then you got to be able to pick out N and R. Okay? Let's look at, we got one other rule and one more example. And we will be done for today. Permutation rule when objects are alike. Okay? The number of permutations of n objects in which K1 objects are alike, K2 objects are alike, etc., is n factorial over K1 factorial, K2 factorial, and so forth, all the way to KP factorial. Where we do have to add this side note, K1 plus K2 plus ... plus KP equals N. Now, this will make way more sense when we do example 8, okay? Example 8 says, find the number of different passwords using all of the letters in the word Massachusetts. Okay? So, find the number of different passwords using all of the letters in the word Massachusetts. Okay, so here's the deal. You have n letters, n number of letters in that word, and you're choosing all of them. The thing that makes it different, why we can't just say in factorial like we did with the 14 teams was an in factorial because we had 14 teams. We were choosing all 14 teams. Okay, this is a word with, I think it's 13 letters. We're choosing all 13 letters, but the problem is some of those letters repeat, like S repeats and T repeats, okay? So that makes it a little more tricky, okay? That's why we use the formula up there, is if something in there is repeating. Now, this really only works for, like, problems like this. This doesn't mean that if any of it can repeat, because then that turns into a combination, okay? So just use this when they tell you you have this word and we got some passwords we got to make and some letters to repeat. What's N? N equals 13, right? There's 13 different letters in that word. M-A-S-S-A-C-H-U-E-T-T-S. Is there 13? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yes. Doesn't mean different. It means how many letters are used in that word. Okay? All right. Then we need to pick out how many M's do we have? Just one, right? Okay. Yeah. It's not a trick question, I promise. How many A's are there? 2. How many S's?
4.
C's?
1.
What is that? H?
1.
U?
1.
E?
1.
And T. Good. And what they're saying about the K1 plus K2 plus blah, blah, blah equals N, if we add up M-A-S-C-H-U-E-T, it makes 13. Okay, that's what they're saying there. Now, we just need to use our formula. So I'm going to have 13 factorial over, all right, each one of the letters as a factorial. So that's going to be 1 factorial times 2 factorial times 4 factorial. Then I have 1 factorial 4 more times. 1, 2, 3, 4, and then a 2 factorial. Guys, all those 1 factorials make what? 1. 1 factorial is just 1, guys. Okay? So they're all going to make 1. 1, 2, 3, 4. There we go, 5. So that's going to leave me with 13 factorial over 2 factorial times 4 factorial times 2 factorial, right? You can put that in the calculator. You're going to want to put that in the calculator. If I go over here, I do a split, go over here, that's going to give me, let's look, I'm going to stack them, 13 factorial, yeah, there we go, over 2 factorial, 4 factorial, and 2 factorial. Yep.
So what do we do with all the ones?
They make 1. They just turn into 1.
All of them?
Because they're being multiplied. Yeah.
So
This
they
is,
just cancel out. There's no need.
yeah, there's no need. Because it's just, 1 factorial is 1. So that's 1 times 1 times 1 times 1 times 1. And then 1 times 2 factorial times 4 factorial times 2 factorial is just 2 times 4 times 2 factorial. Okay? Yeah, they just kind of cancel out. That's going to give me, what do I get? 64,864,800. Different passwords. Possible different passwords if I use all the letters in the word Massachusetts. Okay? Taking all the letters. Okay. The only other thing that I want to, I don't think, because it's nearly time to go. There's some homework questions. Here's the deal. You want it says something like this, okay? We want a 6-digit passcode. It says something like, how many possibilities are there for a 6-digit passcode? Okay. Well, here's the deal. You've got to know how many using, it'll say something like using single digits. It may not even say using single digits. But here's the deal, guys. You got to know how many possibilities, 1, 2, 3, 4, 5, 6, there are, okay? So you're going to make a 6-digit number, 6-digit passcode, but what all can go in slot 1? See, that's where you're going to get it wrong. Well, it's 0 through 9. You have to count 0. So there's actually 10 possibilities that can go in that slot. So, because there's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 10 possibilities that can go in that slot. So if we do it without repeating, okay, we can't repeat. So there's 10 possibilities in the first slot, 9, 8, 7, 6, 5, right? That's without repeating, okay? But the key is you have to know, yes, because there's 10 possibilities in the first slot, because 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, okay? Now you used one of those, so how many possibilities are there in the second slot? It'll be easier if I do it like that. Now there's 9. Then I take out, now how many are in the third slot? 8 different possibilities, okay? Now with repeating, okay, let's say we can repeat, we're still doing 6 digits. 1, 2, 3, 4, 5, 6. Okay, I have 10 possibilities in that first slot. I can repeat this time. So how many are in the second slot? 10. 10, 10, 10, 10. Guys, this is really, if you want to help yourself in the calculator and save yourself time, this is 10 to the 6th power. Okay? Because 10 times 10 times 10 times 10 times 10 times 10, 6 times is 10 to the 6th. Okay? All right. Just a slight clarification there. I had people that had issues with how many actual digits there are between 0, how many single digit numbers there are. There's 10 single digit numbers. Okay?